Hi, my name is Gagandeep Singh and I'll be presenting NERO, a near high bandwidth memory stencil accelerator for weather prediction modeling. To begin, I will give a high-level summary of the talk. The motivation of this talk is that stencil computation is an essential part of weather prediction applications. Unfortunately, these kernels are memory bound with limited performance and high energy consumption on multi-core architectures. Therefore, our goal is to mitigate the performance bottleneck of complex compound stencils found in real-world weather prediction applications in an energy-efficient way. To this end, we present NERO. NERO is the first near-high bandwidth memory FPGA-based accelerator for representative kernels from a real-world weather prediction application. Our detailed Roofline analysis show weather prediction kernels are constrained by DRAM bandwidth on a state-of-the-art CPU system. We optimize NERO with a data-centric caching scheme with precision-optimized styling for a heterogeneous memory hierarchy consisting of URAM, BRAM, and HBM. Also, we perform in-depth scalability analysis for both DDR4 and HBM-based FPGA boards. In our evaluation, we show that NERO outperforms a 16-core IBM Power 9 system by 4.2 times and 8.3 times for two representative kernels from a real-world weather prediction application. Further, NERO reduces energy consumption by 22 times and 29 times with an energy efficiency of 1.5 gigaflops per watt and 17.3 gigaflops per watt. Here is the outline for our talk today. First, we will discuss the background on stencils. Stencil computations update values in a multi-dimensional grid using a fixed pattern of grid points. To demonstrate, we show a basic 7.3D Jacobi stencil, which is frequently used as a benchmark for stencil study. This kernel accesses 7 elements to perform 6 additions and 2 multiplications at the same time. Stencils are widely used. Around 30% of high-performance computing applications make use of different stencils, including fluid dynamics, image processing, atmospheric modeling, etc. Stencil computations that operate on multi-dimensional grids are cache unfriendly. They have limited arithmetic intensity as there is reuse only in the neighboring pixels. Moreover, stencils have sparse and complex memory access pattern. On the left, we show the stencil pattern of Jacobi 3D stencil, and on the right is the mapping from 3D plane onto 1D plane. To update each grid point, 7 input variables as well as 1 output variable needs to be accessed. From the figure, it is not hard to predicate that without careful design, cache misses caused by the remote access of the array elements would stall the program to a great extent. This complicates the efficient mapping on traditional platforms. Therefore, we see a performance bottleneck. Let's take a look at the stencil computation in a real-world weather application. The Consortium for Small-Scale Modeling, or COSMO, is a weather prediction model currently being used by a dozen nations, including Switzerland, Germany, Italy, etc. The central part of the COSMO model is called the dynamical core or DICORE, which has around 80 different stencil compute motifs with varying amount of access patterns. These stencils make use of around 30 variables and 70 temporary arrays. The figure shows a small section of COSMO CDAC where the blue nodes contain complex composed stencils. These complex stencils are found in other forecasting models as well as such as IFS and ICON. Horizontal diffusion and vertical advection are two complex stencils that are representative of data access patterns and algorithmic complexity of the entire COSMO model. Earlier we showed a Jacobi stencil that is an elementary stencil that we usually come across in literature. However, stencil computations are complex in modern weather applications. To demonstrate the complexity of weather stencils, we explain horizontal diffusion kernel, which is a complex weather stencil from COSMO. Unlike elementary stencils, compound stencils consist of a collection of elementary stencils. Horizontal diffusion is one such kernel that iterates over a 3D grid performing Laplacian and flux operations. The picture over here shows a composition of horizontal diffusion stencil in which a Laplace stencil and first order flux stencil functions are cascaded together. The bottom figure illustrates the data flow of horizontal diffusion using a directed graph, where the black nodes represent the input field and the white nodes represent all the different stencils. The figure shows that each stencil inside a horizontal diffusion has different access pattern. For instance, a single evaluation of the Laplacian stencil accesses the input at 5 offsets. The graph shows that these stencils have complex memory access behavior, which leads to low arithmetic intensity. We have provided more details on Cosmos representative kernels in our paper. Now let's discuss how these complex stencils perform on a state-of-the-art multi-core system. The figure over here shows a roofline plot where the x-axis is the arithmetic intensity, which is flops per byte, and on the y-axis we have performance. We show the peak for an IBM 16-core Power 9 socket with peak DRAM and L3 bandwidth. The single thread performance of vertical advection is shown in blue and horizontal diffusion in green. After optimizing these kernels for the power system using various optimization-based techniques, we achieved 29.1 gigaflops and 58.5 gigaflops respectively for a complete Power 9 socket. We see that their low arithmetic intensity limits their performance, which is 1 order of magnitude smaller than the peak performance and results in a fundamental memory bottleneck that standard CPU-based software optimization techniques cannot overcome. Our roofline analysis revealed that these weather prediction kernels are DRAM bandwidth constrained on a multi-core architecture. Now we will discuss about other platforms that could be used for implementing weather prediction applications. There is a wide range of platforms that provide a trade-off between flexibility and efficiency. In our work, we focus on FPGA-based heterogeneous systems. FPGAs allow us to create domain-specific memory hierarchy, which can handle the irregular memory access patterns efficiently and offer significantly higher memory bandwidth with their on-chip memories. Our heterogeneous system comprises of IBM Power 9 CPU connected to an FPGA board via copy-to interface. In our evaluation, we make use of two FPGA boards. First is Alpha Data 9H7 with HBM memory, and the second is Alpha Data 9V3 with DDR4. Our CPU FPGA heterogeneous platform offloads the representative weather kernels onto the FPGA, where 98% of execution happens. Now we annotate the FPGA rooflines to our earlier CPU roofline plot to show the potential of FPGA boards. For Alpha Data 9V3 card that has DDR4 as DRAM, we have performance peak at 0.97 teraflops. The roofline of Alpha Data 9H7, which has HBM memory, is at 3.6 teraflops, with HBM bandwidth of 410 gigabytes per second. Apart from this tremendous potential, FPGAs also allow us to tailor the circuitry and build application-specific heterogeneous memory hierarchy, which we exploit in our design. Now I will present our key contribution. Considering the challenges weather kernels face on the conventional architectures, our goal is to mitigate the performance bottleneck of these kernels in an energy-efficient way. To this end, we present NERO. NERO is the first HBM FPGA-based accelerator for representative kernels from a real-world weather prediction application. We optimize NERO with a data-centric caching scheme with precision-optimized styling for a heterogeneous memory hierarchy consisting of URAM, BRAM, and HBM. Our contribution also includes in-depth scalability analysis for both DDR4 and HBM-based FPGA boards, where we change the number of memory ports and processing elements. Now we will go into the details of the architecture and data flow sequence of NERO. The weather data based on the atmospheric model resolution grid is stored in the DRAM of the host system. As the FPGA has limited resources, we propose a 3D window-based grid transfer from the host data to the FPGA, facilitating a smaller and a less power-hungry deployment. The window size represents the portion of the grid a processing element would process. We employ the double buffering technique between the CPU and the FPGA to hide the transfer latency. We configure a buffer of 32 cache lines between the Axie4 interface of copy2 and the FPGA to exploit the copy2 bandwidth. On the FPGA side, following the initial buffering, the transfer grid data is mapped onto the HBM memory. The FPGA consists of two HBM stacks, each having 16 memory channels. A channel is exposed to the FPGA as a 256-bit wide port, and in total, the FPGA has 32 such ports. In this work, we enable a single HBM stack based on our resource and power consumption analysis for the vertical advection kernel. The HBM port provides 256-bit data, which is half the size of copy2 bit width. Therefore, to match the copy2 bit width, we introduce a stream converter logic that converts an HBM stream to a copy-compatible stream. From the HBM, a processing element reads a single stream of data that consists of all the fields that are needed for a specific Cosmos kernel computation. Fields represent atmospheric components like wind, pressure, velocity, etc. The processing elements use a field stream splitter logic that splits a single HBM stream to multiple streams, one for each field. However, as there is only a single output stream for all the weather kernels, we do not need extra logic to merge the streams. In our design, we use a switch which provides the capability to bypass the HBM when the grid size is small and map the data directly onto the FPGA's URAM and BRAM. We build an application-specific memory hierarchy by tailoring the cache levels and cache sizes to our kernel's memory access patterns. We make use of memory reshaping techniques to configure our memory space with multiple parallel BRAM or URAMs. We form an intermediate memory hierarchy by decomposing or slicing the 3D window data into a 2D grid. This allows us to bridge the latency gap between the HBM memory and our accelerator. Vertical advection is more computationally complex than horizontal diffusion as it has dependencies in the Z dimensions. Therefore, we demonstrate our design flow by means of vertical advection kernel. As shown, the main computational pipeline of vertical advection consists of a forward and a backward sweep logic. The forward sweep results are stored in an intermediate buffer to allow for backward sweep calculation. Upon completion of the backward sweep, results are placed in an output buffer that is followed by a degrading logic. The degrading logic converts the calculated results to a 512-bit wide output stream. To optimize the processing element, we apply various optimization strategies which are mentioned in our paper. This is a complete design flow of NERO. All the tasks are executed in a data flow manner that enables task-level parallelism. We also build an application framework to support our architecture design. NERO communicates to CPU over a high-performance cache-coherent copy-to interface, where NERO is acting as a peer to the CPU by accessing the main memory through PSL, which is the copy endpoint on an FPGA. Our Cosmos API handles the offloading jobs to NERO with an interrupt-based queuing mechanism. This allows for minimal CPU usage during FPGA operation, thus low power consumption. We make use of Snap framework that allows for seamless integration of the Cosmos API. In our application framework, the job manager dispatches jobs to streams, which are managed in the stream scheduler and fetch data through DMA transfers. Please refer to our paper for more details on our application framework. I will now describe our precision-optimized styling scheme. As mentioned earlier, the window size represents the portion of the grid a processing element would process. The best window size is critical in terms of area versus performance trade-off. Further, selecting an inappropriate window size leads to suboptimal results. However, most FPGA developers manually optimize for the right window size and often adapt the design to use homogeneous tile sizes. However, manual optimization is tedious because of huge design space and it requires expert guidance. Therefore, instead of pruning the design space manually, we formulate the search for the best window size as a multi-objective auto-tuning problem, taking into account data type precision. We make use of OpenTuner, which uses machine learning techniques to guide the design space exploration. I will now discuss the effect of different tiling with different precision. Our auto-tuning technique tries to determine a Pareto optimal solution in terms of performance and resource utilization for our 3D window dimensions. Here we can see single precision results for vertical advection for a single processing element. We get a wide range of performance versus resource utilization points for different tile sizes. By using the auto-tuning approach and our careful FPGA microarchitecture design, we can get a Pareto optimal result with a tile size of 64 by 2 for single precision vertical advection. Also, you can see here that the hand-tuned designs are suboptimal compared to our auto-tuned results. However, for half precision, we get a different tile size of 32 by 16 to get our Pareto optimal point. As we can see, a good tile size for a single precision might lead to poor results when used with half precision. Therefore, the Pareto optimal tile size depends on the data precision, and it is critical to find the right size that maximizes the performance with minimal resource utilization. We employ a similar strategy for horizontal diffusion, and you can find those results in our paper. Now I will present our evaluation results for performance analysis. First, we discuss single precision performance results for the vertical advection. We implement our design on both an HBM and DDR4 based FPGA board. We perform in-depth scalability analysis where we scale the number of processing elements and analyze the change in execution time. For the DDR4 based design, we can accommodate only 4 processing elements on the 9v3 card, while for the HBM based design, we were able to fit 14 processing elements before exhausting the onboard resources. We make 4 observations from the figure. First, for a single processing element which fetches data from a single memory channel, the DDR4 based design provides higher performance than the HBM based design. This is because the DDR4 based FPGA has a larger bus width than an HBM port. This leads to a lower transfer rate for an HBM port. One way to match the DDR4 bus width would be to have a single processing element fetch data from multiple HBM ports in parallel. However, using more ports leads to higher power consumption. And our experiments show that this power consumption is around 1 watt per HBM port, which is allowed. Second, as we increase the number of processing elements, we observe a linear reduction in the execution time for the HBM based design. This is because we can evenly divide the computation between multiple processing elements, each of which fetches data from a separate HBM port. Third, in the DDR4 based design, the use of only a single channel to feed multiple processing elements leads to congestion issue that causes a non-linear runtime reduction. As we increase the number of accelerator processing elements, we observe that the processing elements compete for a single memory channel, which cause frequent stalls. This phenomena leads to worse performance scaling characteristics for the DDR4 based design as compared to the HBM based design. Fourth, our full-blown FPGA HBM based vertical advection implementation takes 1.1 milliseconds to execute, which is 120.7 gigaflops per second. For horizontal diffusion implementation, we achieve 0.42 milliseconds, which is 485 gigaflops. We also report half precision results in the paper. By carefully designing the microarchitecture with application-specific heterogeneous memory hierarchy, NERO is 4.2 times and 8.3 times faster for vertical advection and horizontal diffusion respectively than a complete Power 9 node. We also did energy efficiency analysis for our design. Figure over here shows the energy efficiency, which is gigaflops per watt for vertical advection on the HBM and DDR4 based design. We make 3 major observations from the figure. First, the DDR4 based design is more energy efficient than the HBM based design when the processing element is small. This observation is in line with our discussion about processing elements performance with small processing element count. However, as we increase the number of processing elements, the HBM based design provides better energy efficiency. This is because more data can be fetched and processed in parallel via multiple HBM ports. Second, kernels like vertical advection with intricate memory access pattern are not able to reach the pre-computational power of FPGA. The large amount of control flow in vertical advection leads to large resource consumption. Therefore, when increasing the processing element count, we observe a high increase in power consumption with low energy efficiency. Third, we achieve an energy efficiency value of around 1.5 gigaflops per watt with 14 processing elements for vertical advection kernel. Therefore, we conclude enabling many HBM ports might not always be the determining factor to reach the target parallelism and energy efficiency. On the other hand, for horizontal diffusion, which is highly parallelizable in all the dimensions and has limited control flow, the energy efficiency keeps increasing with increase in processing elements count. By executing these kernels on an HBM-based board, we reduce the energy consumption by 22 times for vertical advection and 29 times for horizontal diffusion compared to a 16-core Power 9 socket. And NERO provides energy efficiency of 1.5 gigaflops per watt and 17.3 gigaflops per watt. Now let me conclude. The motivation of this talk is that stencil computation is an essential part of weather prediction applications. Unfortunately, these kernels are memory bound with limited performance and high energy consumption on multi-core architectures. Therefore, our goal is to mitigate the performance bottleneck of complex compound stencils found in real-world weather prediction application in an energy-efficient way. To this end, we present NERO. NERO is the first near-high bandwidth memory FPGA-based accelerator for representative kernels from a real-world weather prediction application. A detailed Roofline analysis show weather prediction kernels are constrained by DRAM bandwidth on a state-of-the-art CPU system. We optimize NERO with a data-centric caching scheme with precision-optimized tiling for a heterogeneous memory hierarchy consisting of URAM, DRAM, and HBM. Also, we perform an in-depth scalability analysis for both DDR4 and HBM-based FPGA boards. In our evaluation, we show that NERO outperforms a 16-core IBM Power 9 system by 4.2 times and 8.3 times for two representative kernels from a real-world weather prediction application. Further, NERO reduces energy consumption by 22 times and 29 times with an energy efficiency of 1.5 gigaflops per watt and 17.3 gigaflops per watt. We conclude that hardware acceleration on an FPGA plus HBM fabric is a promising solution for compound stencils present in weather prediction applications. We hope that our insights and observations would inspire developers of different high-performance computing applications that suffer from similar performance bottleneck. Thank you for listening to my talk. For more details, I invite you to read our FPL 2020 paper.